I am Vivek Bajpai. Now I am starting my class of maths, real number, class 10th CBSE board. Here we start with the division algorithm lemma. Lemma is a proven statement used for proving another statement. Here Euclid division lemma is A is equal to BQ plus R. A is dividend, B is divisor, Q is quotient, R is remainder. Again we comes to next thing. Let we divide 123 by 14. We get 14, 123, 8 times 112, 11 left. By the lemma, dividend is equal to 123, divisor is equal to 14, quotient is 8, remainder is 11. Now example number 2, a number when divided by given as quotient and remainder, just like a number when dividend is to be find, we have 24 as a quotient and 17 as a divisor, 15 as a remainder. We have to find the number. Here we write first the division algorithm lemma. Dividend is equal to divisor into quotient plus remainder. 17 multiplied 24 plus 15, it is 408 plus 15, it is 423. Hence the remainder required number is 423. Using Euclid division lemma, example number 2, find HCF of the number 1025 divided 37. We find HCF of the number 1025 and 37. When we divide 37, the answer is quotient is 27 and remainder is. By the lemma 1025, 37 into 27 plus 26. Then again we divide this number. We find 37 is equal to 26 into 1 plus 11. Again we divide 11 by 26. We get 11 2s are 22 and 4 as a remainder. 26 is equal to 11 into 2 plus 4. Each and every time you have to write the division algorithm. 4 divided by 11 we get 2 and remainder is 3. 11 4 into 2 plus 3. 3 is 3 divided by 4. Then we get this 4 is equal to 3 into 1 plus 1. Then 1 is divided by 3. Ultimately 3 is equal to 3 into 1 plus 0. Each and every time you have to carefully study this question, that when the remainder finish, then HCF comes. If the HCF of 65 and 117 can be written as 65m minus 117, find the value of m. First we find the HCF of 65 and 117. We divide 65, we get 1 as a quotient and 52 as a remainder. 117 is equal to 65 into 1 plus 52, that is the division algorithm. Then again we by the remainders we have 52 divided by 65, we find 1 as a, then again we write the division algorithm. 65 is equal to 52 into 1 plus 13 in divided by 52, we get 0 as a remainder, so that the question is finishes and the HCF is comes. 52 is equal to 13 into 4 plus 0. 65m minus 117 is equal to 13. Then 65m is equal to 117 plus 13. It is 130. M is equal to 130 upon 65. It is 2. M is equal to 2. By the lemma, Find SCF of 1651 and 2032. Express the SCF in the form of 1651m plus 2032n for some integer m and n. We get by lemma 1651 divided 1 times and we get 381. 1651 into 1 plus 381. 381 4s are 1524 and remainder is 127. 1651 is equal to 381 into 4 plus 127. We get 127 and this is 3. Quotient is 3. Now the remainder is 0, then it is SCF is founded. From second equation, we get 1651 is equal to 381 into 4 plus 127. This is the way to find the M and N. 1651 381 into 4. Then first to see that 1651, this one, is equal to 381 into 4 plus 127. We take these two numbers the left side. Then we write 127 is equal to 1651 minus 381 into 4. 1651 minus 2032 minus 1651 into 4. What is this? The 381 is a difference of these two numbers. What we write in the terms of question. 2032 minus 1651. 1651 minus 2032 into 4 minus plus 1651 into 4. 1651 1 time, 4 time here, it is 5 times. 5 into 1651 plus, sorry, it is minus here on 2032 and this minus comes here also. Then n is equal to minus 4. These sums are lengthy and subjectical. You have to write so many lines. So you have to learn these lines also. You have to learn these lines each and every time. If you does not write these lines, you doesn't get any number. That prove that n square plus n is divisible by 2 for any positive integer. Any positive integer n, any positive integer n is of the form 2m or 2m plus 1, where n is equal to 2m. So in place of n we have to write 2m and this is the square of it and plus 2m. 2m whole square is equal to 4m square plus 2m is equal to, and then it is, we take 2m common, then it is 2m plus 1. N square plus n is equal to 2r. So what is r? Because this number, this complete number is m, 2m plus 1 is r. It is a positive integer. So that n square plus n is divisible by 2. Next case, if we take, first we take 2m, then again we take 2m plus 1. Then in place of n, we write this number 2m plus 1 whole square plus 2m plus 1. So we get, we will not solve this number, but to take 2m plus 1 as a common, and then what is left here? 2m plus 1 plus 1. Means 2m plus 1 and 2m plus 2. This number, if you take out 2 also, then 2m plus 1 and m plus 1. And as is this 2m plus 1 and m plus 1. These things each and every time you have to carry in your mind. These things you have to carry. These things. This. Each and every time you have to carry these things carefully. N square plus n is divisible by 2. Hence, n square plus n is divisible by 2 for every positive integer n. Next, sum. Show any positive integer is of the form 3q or 3q plus 1 or 3q plus 2 for some integer q. If you go back to these sums, similar things are being happened. Let n be any arbitrary positive integer. On dividing n by 3, let q be the quotient and r be the remainder. Then by Euclid lemma, n is equal to 3q plus r, where r is less than or equal to 0, or r is greater than or equal to 0, or less than 3. These three numbers for some integers, thus any positive integers of the form 3q, 3q plus 1 or 3q plus 2 for some integer q. Next, example number 4. Example number 4, show that every positive integer is of the form 4q plus 1, 4q plus 3 for some integers. Now see that 1, 3. You have to consider these things also. And each and every time when you solve the questions, you have to write these lines also. Here, let n be any arbitrary odd positive integer. When we divide it by n by 4, let q be the quotient. If you divide this number by 4, what you get? You get only q. And r be the remainder. By Euclid lemma, we have n is equal to 4q plus r, where r is greater than or equal to 0 or is less than 4, n equal to 4q or 4q plus 1, 4q plus 2, 4q plus 3. Clearly, 4q and 4q plus 2 are even. Understand this. 4q and 4q plus 2, these two numbers are even. And 4q plus 1 and 4q plus 3 are odd. So these are even, and since n is odd, we have n is as not equal to 4q. So if n is not equal to 4q, then necessarily n is not equal to 4q plus 2 also. So that n equals to 4q plus 1 or 4q plus 3 for some integer q. If the number is not even, then it is odd. Hence, any positive odd integer is of the form 4q plus 1 or 4q plus 3 for some integer q. Next sum. Example number 5. If n be any odd integer, show that n square minus 1 is divisible by 8. So by solution, we know that every odd integer is of the form 4q plus 1 or 4q plus 3 for some integer q. Case 1 means this one, when n is equal to 4q plus 1. In this case, we have n square minus 1, 4q plus 1 whole square minus 1 is equal to 16q square plus 8q. We take out 8q plus bracket 2q plus 1, which is divisible by 8. Case 2, when n is equal to 4q plus 3, in this case n square minus 1 is equal to 4q plus 3 whole square minus 1. It is 16q square plus 24q plus 9 minus 1, 16q square plus 24q plus 8, 8 2q square plus 3q plus 1. Hence, if n is an odd integer, then n square minus 1 is divisible by 8. Here we show that any positive even integer is of the form 4q or 4q plus 2, where q is some integer, taking n be an arbitrary even positive integer. Why we take this? Because it is 4q and 4q plus 2 even number, so that we have taken this. On dividing n by 4, let q be the quotient and r be the remainder. Then by Euclid lemma, we have n is equal to 4q plus r, where r is greater than or equal to 0 or less than equal to 4. Then n is equal to 4q or 4q plus 1 or 4q plus 2 or 4q plus 3. 4q plus 1 and 4q3 are odd. Since n is even, we have n is not equal to 4q plus 1 and 4q plus 3 not equal to. Each and every time. Here the concept is based on one thing is not true, then other is true. You have to learn these things. N is equal to 4q, so n is equal to 4q or 4q plus 2 for some integer q. Hence any positive integer is of the form 4q or 4q plus 2 for some integers. Here show that any positive odd integer is of the form 6m plus 1, 6m plus 3, 6m plus 5. You can see that these numbers are odd when m is some integer. Let n be a given positive odd integer on dividing n by 6. Why n by 6? Each and every time see that 6, because 6 is here, so that we divide n by 6. Let m be the quotient and r be the remainder. Then by Euclid lemma n is equal to 6m plus r, where r is greater than or equal to 0, less than equal to 6. So n is equal to 6m plus r, where r is anything 0, 1, 2, 3, 4, 5. Then n is equal to 6m or 6m plus 1 or 6m plus 2 or 6m plus 3, 6m plus 4 or 6m plus 5. Thank you. We divide this part into 2, so that next part is coming on the next day. And thank you for watching my channel. Please like, subscribe and share. And I also want that you will see my channel and encourage me.